Oh, today we are going to be starting to answer a question I've been wanting to look at and answer for quite a bit. I believe I was from a Matt Parker video I watched where he talked about this, and I always want to go through it just for fun and, to work on my critical thinking skills. And the thing here is we're trying to figure out in a grid, n by n, how many squares there are. The final thing actually is going to be rectangles rotations. Um, how many of those can possibly be put in that grid? But we're going to start simple with squares no rotations. Then we're going to head to both squares with rotations and rectangles without rotations. We're going to combine from what we learned there to try and solve the rectangles with rotations. So let's start with the first one. How many squares are in an n by n grid? We don't rotate these squares. Well, 1 by 1, that's 1. 2 by 2 has 4 1 by 1s. And 1 2 by 2. 3 by 3 has 9 1 by 1s. 4 2 by 2s. And 1 3 by 3. Now, as you can see, there's some patterns here. First off, we can notice, like, there seems to be 1 4 9, which are powers of, I'm sorry, not powers, but basically they're squares. 1 2 square, 3 square. So we see basically two things right here. For an n by n grid, there should be n squared 1 by 1 squares. So there should be 1 for the 1, 9 for the 3, because 3 times 3, 9, 9 1 by 1. And yeah, because 1 for each square. That makes perfect sense. And for an n by n grid, there also should be one n by n square. The 1 by 1 is 1 by 1, 2 by 2, 1, 2 by 2, 3 by 3, 1, 2 by 3 by 3. So the last thing to ask is in between, right? In between n and 1. Because we know in an n by n grid there's one n by n square and 1 by 1 squares, but let's say we had a random one m in between there. Well, let's just designate for an m by m square, we'll just designate the corner as the key square. This key square basically makes it so the position of this key square is denotes a unique square, right? So this here denotes this one, while this here denotes this one. And so we know for each red dot, basically each square that we can dot in for, while being able to then draw the rest in, that will be a square that fits into the n by n grid. So we just, if we can make a shape, for example, that here we're making a square, well, we know it's a 2 by 2 square, so we know that there's 4. We can easily count that as well. What we also notice, however, is, well, it's producing a square, which is interesting because if we go further, we realize that in a 4 by 4 there is 9 2 by 2s. And if we imagine here an extra one, well, let's look at this. From the key square, it must have a square below it, diagonal to it, and beside it. The only squares that don't have that are these edge squares. So if we had a 4 by 4, we'd have the edge squares here. Well, then this square actually here would all be able to have red dots. So it would be then a 3 by 3. If we go one higher, the length of the squares goes one higher. So we get to see that the following is true. The amount of n by n squares in a grid of n by n is equal to n plus m minus 1 squared. Why? This is m right here. y minus 1. We don't count this square. We don't count the key square. And this is n. Basically, if we take 1 off of this, these are the places where the key square can't be. But if this was too long, then we want to take 2 off. For example, if this was a 3 by 3, we take 2 here and 2 here off, and only this corner would be left. And that's because there's only one 3 by 3 that can fit in a 3 by 3. So that's where we get that m minus 1, because we're not counting the key square. That, subtracted from each edge, gives us a square of size n plus m minus 1. And the area is that square, which is equal to n plus 1 minus m squared. So, how do we get the entire thing? Well, we need to start, we know that 1. Well, for 1, it's n squared, n squared, n squared, squares. Well, let's just put 1 in here into this equation, as we see for m. It just equals n squared. We also know for m equals n, well, m minus n, that's 1 squared. Which is like the fact that we see the 1 squared is that there's 1 by 1, 1 2 by 2, 1 3 by 3. And the fact that the plus 1 gets knocked out by the mod, m equals 1, it's just n is 1, 4, 9, which is, 1 for each. So we see, and then this other fact from here is just built in. We just replace m with I, because we need to go through every m by m square. And this is the final equation per the question. The summation from I starting at 1 all the way to n with m plus 1 minus I squared is how many squares there are in an m by n grid if you don't allow them to rotate. Which finishes our first section with squares and no rotation.